Hey, welcome back everyone. I want to talk about another application to physics. This one is center of mass. So center of mass. And to begin with, we need to discuss Archimedes' principle. So here's what Archimedes says. If we have a couple of masses, so if masses m1 and m2 are attached to a rod at distances d1 and d2 from a fulcrum. So let me draw the picture and then I'll finish off the sentence. So we've got a couple of masses. So let's say M1 and M2. So M1's here, M2 is here at distances from a fulcrum. So that's this point right here. So there's D1 and there's D2. All right, so let's say that we have this setup, and notice that I've drawn the picture as if our seesaw here is horizontal. Well, Archimedes' principle actually tells us when this will be horizontal. So if they're attached at distances d1 and d2 from a fulcrum, then balance is attained, meaning this will be horizontal when d1 times m1 is equal to d2 times m2. Right? So that's Archimedes' principle. And you've seen this if you've ever sat on a seesaw. If you have a big kid and a little kid sitting on a seesaw, both of them at the end, right? Then what happens? The big kid goes down, the little kid goes up. If you want to get balance, what do you do? Well, you have the big kid move in closer, and as he moves in closer, right, it starts to get into balance, right? And by moving him in to the appropriate distance, the distance for which these two match, right, for which this equation holds, then you'll have the seesaw be balanced out. Now, I want to put this into a sort of more mathematical context. So if the rod is the x-axis, let's say, let's call it x bar. X bar is the center of mass. The center of mass is the spot where the fulcrum needs to be, right, to ensure that we have balance. And the masses are at so let's say what I want to do is put this setting onto the x-axis. So the masses are at x1 and x2. So now let's draw the picture. I've got mass 1 at position x1. I've got mass 2 at position x2. And then the center of mass, the spot where the fulcrum would be, is going to be, we'll call that position x bar. Okay, so what we need for balance then is I need this distance times m1 to equal this distance times m2. So what we would have then is, let's see, so the distance between x1 and x bar, that's x bar minus x1 times m1, that has to equal the distance here, that's x2 minus x bar times m2, right? So there is Archimedes' principle setup, right, based on this picture right here, this diagram. So let's see now. What I want to do is actually solve for x bar. So if we multiply things out, we'll get an x bar m1 minus x1 m1 equals x2 m2 minus x bar m2. And then let's see, I want all the x bar stuff on the left-hand side. So we'll have x bar times m1 plus x bar times m2 equals x1 m1 plus x2 m2. I'm going to factor an x bar out of each piece, so that'll be x bar times m1 plus m2. And then that's going to equal to, and I don't know why I did this when I multiplied these things out. I really want the m1 in front of the x1 and the m2 in front of the x2. So I'm not doing any tricks. I'm just rewriting that m1 x1 plus m2 x2. And now, if we solve for x bar, so x bar is going to be m1 x1 plus m2 x2 divided by m1 plus m2. So what this formula does for us is it says, all right, if you take your mass 1 and put it in x1, your mass 2 and put it in x2, this formula tells you exactly where to put x bar. It tells you what number x bar is going to be. And now you can generalize this. So more generally, so if instead of putting just two masses, let's say you want to put a bunch of masses, you can generalize this formula. So more generally, if masses m1 up through m sub n are at positions x1 up through xn, then x bar has the following formula. So it'll have a numerator, which will be the sum, I equals 1 to n, mi xi, divided by the sum of the masses, so sum I equals 1 to n m sub I. So what we've done right now is we've and I should let me put the x bar so that it's centered better, right? So there's the formula for x bar in general. What we've done is we've talked about center of mass now in the one-dimensional case when all of the masses are in a line. Now we'd like to move this to the two-dimensional case. So 2D case. Now we're going to arrange our masses. So let's say if masses m1, m2 dot 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 up to m sub n are at the following positions, x1 comma y1. Now we're going to be arranging them in the plane, the two-dimensional setting, rather than on a line. So x1 comma y1 up through x sub n comma yn. Then there's a couple of terms that I want. So then the moment about the x-axis is, and we write this as capital M sub x, and by definition, it is going to be the sum I equals 1 to n of m sub I times y sub I. There's also the moment about the y-axis, so about the y-axis, and that we write as capital M sub y, and it's the sum I equals 1 to n m sub I times x sub I. Now it kind of looks like I made a mistake here, right? The moment about the x-axis we write as capital M sub x, but then notice it's got just the y-coordinate, y sub I in there. And the moment about the y-axis, m sub y, has x coordinates in the formula. It's not a mistake. That is correct. There's also the mass. So the mass is, and we'll write that as a little m, it's the sum of all the masses. So sum I equals 1 to n m sub I. Now, so now then the center of mass is the point x bar comma y bar, and I need to tell you how to find x bar and y bar. So where x bar is equal to m sub y divided by little m, and y bar is equal to m sub x divided by little m. So if you want to find the center of mass of a two-dimensional system, compute the moments, compute the mass, and then set up these fractions right here, and that'll tell you exactly who the center of mass is. Now, one thing, before I go on, I'm going to do an example in a second, but a couple of things that I want you to notice. First of all, our one-dimensional formula for x bar, here it is right here. And notice, who is that right there? That's the sum masses times x coordinate. That's exactly what we're calling m sub y in this situation right here. So in the two-dimensional system, the numerators and denominators for the center, for the x and y coordinates of the center of mass, take on exactly the same format as they did in the one-dimensional case. We're just extending it to 2 dimensions. Now, so one more thing I want to point out. When we're computing the moment about the x-axis, and you can think of the moment about the x-axis as its tendency to rotate with respect to the x-axis, right? So if the x-axis is moving in this direction, if you put more mass in front of the x-axis than behind it, what's going to happen? Well, it's going to tend to rotate forward, right? If you put more stuff behind the x-axis, then it's going to tend to rotate backwards. And so you would get a positive moment in the case that it's going to rotate towards the front, towards the forward, and a negative if it's going to rotate backwards. So now what does this measure? So if I took an x sub I comma y sub I right here, what does the x coordinate actually measure? The x coordinate measures the distance to the y-axis. So that's where this part is coming from right here. Right? Same thing. So m sub x, we want to characterize the tendency for it to rotate about the x-axis. And so what we have then is we want to measure, when we do y sub i's, we are measuring the distance from that point to the x-axis. Okay, so now let's try an example of computing the center of mass. So let's say that we've got masses as follows. So we've got a mass of 2 at the point 0, 1. We've got a mass of 3 at 1, minus 2, and a mass of 4 at negative 3, 2. And what we want to do is find the center of mass, and so we need to compute some moments and some and the mass. So first, let's compute m sub x. So m sub x is going to be the sum of the masses times the y coordinates. So it's going to be 2 times 1 plus 3 times minus 2 plus 4 times 2. So that comes out to be 2 minus 6 plus 8. And so that looks like 4. And then we need to do m sub y. So that's going to be masses times x coordinates. So m sub y is going to be 2 times 0 plus 3 times 1 plus 4 times minus 3. And so that will give us negative 12 plus 3 is a negative 8. We also need to compute little m. That's the sum of the masses. So 2 plus 3 plus 4. And so that equals 9. I knew something was weird here. Okay, sorry. Negative 12 plus 3. Sorry, that's negative 9. All right, so now to find the center of mass, we just set up the appropriate fractions. And so we will have x bar is equal to m sub y divided by little m. So let's see, m sub y is negative 9, and so we'll get a negative 1. And for y bar, we get 4, so that's m sub x over little m. That's going to be 4/9. So let's see if this actually makes sense. Let's draw the picture now. We have a mass of 2 at the point 0, 1. So over 0, up 1. All right, so we put a mass of 2 right there. We have a mass of 3 at 1, comma, minus 2. So there's a mass of 3 right there. And then at negative 3, comma, 2, we put a mass of 4. So if you take these masses and imagine now, what is the center of mass? If you could take this picture and hold it horizontally, what we want to do is find the balancing point. Right? So if you imagine taking these masses, where would you need to put the balancing point? So our computation right here tells us, let's see, it's negative 1 and then 4/9 is about 1/2. So right about there is our balancing point. So hopefully this makes sense, or this answer makes sense based on your geometric intuition. Okay, so now we'd like to generalize this. Or I guess I shouldn't say generalize it. We want to take this idea now, and instead of working with point masses, what we want to do is work with an actual solid piece of, say, metal or cardboard or something that's been cut out, some irregularly shaped object. But we don't have point masses, we have the mass smeared throughout, distributed throughout the object. So it goes like this. So suppose we are given a thin plate, also called a lamina. It occupies this region, so occupying a region R in the plane, where R is bounded by the graph y equals f of x, y equals g of x, and then the lines x equals a, and x equals b. So it's our usual picture. Sorry, I just want to check one thing. I want to see the symbol that they use in your book. Okay. So here's the picture we got. So let's see. It's our usual shape, like this. Right. So our region R is this region that you can see right here. So imagine taking this, and that it's an actual physical object that you could take and cut it out, right? Maybe it's made out of metal or cardboard or something like that. You could pull it out. Our goal is going to be to find the balancing point, the center of mass of this irregularly shaped object. And I don't really have a good prop here, but let's say if you got something like this, right? You're looking for the spot where you could put your finger and hold it and keep it balanced horizontally. Right, so we're looking for that balancing point. suppose that the density of the plate is given, or is constant rho throughout. And remember, what is density? In this case, it's going to be mass per unit area. Okay, so here's our setup. We've got this thin plate or lamina bounded by these regions right here. We need to assume that these functions are continuous as usual, and that the density, the amount of stuff that has been distributed throughout this thing, has been done so in a uniform way, right? So that the density is constant. Okay, so now we'd like to solve this problem in the usual way. Our goal is to find the center of mass. All right, in fact, let's write this down. So goal, find the center of mass. And the way we're going to do this is we're going to approximate it first. So we're going to partition. I'll write down the steps in a second. So in this case, I've chopped it up into 4 pieces. But in general, we're going to partition. Right. So this is step 1. Partition AB as usual. So we'll have A equals x0 less than x1 dot 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 less than xn equal to B. Now, and as usual, these will be into lengths delta x. So into subintervals of length delta x. Second step, now if you remember, our next step is always to choose a point in each of those subintervals. Sometimes we choose the points at random, but if we need to be specific, we can. In this case, I want to choose midpoints. So let's let x sub I star be the midpoint. So that's going to be x sub I minus 1 plus x sub I divided by 2. All right, so that's a midpoint. So what I do is for each of these subintervals, go through and mark. So there's x1 star, x2 star. Sorry, my picture's a little bit crowded. There's x3 star. Whoops, sorry. x3 star is really down there. And then x4 star is right there. Okay, so what this does is it allows us to form some rectangles. So you would go up, hit each of the graphs, draw little horizontal line segments, and that's going to create our rectangle. So this is all stuff that we've done several times already. Like that. Okay, so let me finish this and form the rectangle. Let's call it R sub I with height. Well, the height will be f of xi star minus g of xi star, and base delta x. Okay, so now the mass of each of these rectangles, so the mass of Ri is approximately well, let's see, how do you compute mass? It's going to be the density times the area. And so let's see, the mass is approximately rho times the area, which is height here. So that'll be a F of xi star minus g of xi star times delta x. So this, you could say, let's just write that for fun here. Let's call that little m sub I. All right, so the mass within this rectangle is approximately given by this formula right here. Now, what I want to do next is I want to assume that all the mass within a given rectangle is contained right in the middle of the rectangle, like that. So we assume all mass is contained in the center of the rectangle. So what does that mean? Or who is that? How do you find the center? Well, that would mean that it's at that x-coordinate, that's the midpoint. And then, so it's at the center of the rectangle, so that would be at xi star. And then how do you find the midpoint with respect to the y direction, the vertical direction? Add and divide by 2. That's how you find midpoints. And so it would be f of xi star plus g of xi star divided by 2. Now, the reason we're doing this, that we're making this assumption right here, is we would like to then use the formulas that we have for point masses that we developed a little while ago. So, the moments of this system are, so let's see, I need m sub x. That's going to be mass times y coordinate. So it'll be mass times y coordinate. So that's, and it'll be sum of those. So it's going to be sum I equals 1 to n. Rho times f xi star minus gxi star times delta x. Sorry, I'm going to have to erase this part, but I guess that's all right. Times, so what do I have? I have mass, and now I need y coordinate. So there it is, times f of x I star plus g of x I star divided by 2. And I want to clean this up a little bit. I can pull rho as a constant, so I can pull that out. I can pull the 1/2 out also. And so what we'll get is rho over 2 sum I equals 1 to n. Now, if you ignore this delta x, what we have here gives us distance of 2 squares, so, or difference of 2 squares. So this will be f of xi star squared minus g of xi star squared times delta x. All right, so there's the moment with respect to the x-axis. We also have the moment with respect to the y-axis. Let me write that one down here. So m sub y is going to be sum I equals 1 to n. So it's going to be mass times x coordinate. Oops. And the x coordinate is So this will be a x. What am I spacing out here? Oh, right. It's just xi star. Yes, it's the midpoint, but we're calling it xi star, so that's what I need for the formula. And if we fix this up a little bit, let's take the constant out, and so we'll get sum I equals 1 to n xi star f of xi star minus g of xi star times delta x. So here's the moments. There's also the mass. So the mass of the system is little m, and that's just going to be the sum of the masses. So sum I equals 1 to n rho times f of xi star minus g of xi star times delta x. Okay, now these are exactly the three things that we would need if we want to find center of mass. But really, and I guess I shouldn't say the moments are equal to this. These are the moments with respect to the partition, with respect to the point masses. Now, if we want the actual moments, right, and these are really approximations, what we want to do is let n go to infinity in each of these cases. So, when we say the system here, this is the moments of the system of point masses, and now we can define, I wish I had some room here. I'm going to do it right here. So now, the moments of the lamina, rather than the point mass system, are, okay, so m sub x is going to be the limit as n goes to infinity of this. Notice this is a Riemann sum right here, and so it's going to then become an integral, so it'll be rho over 2 integral from a to b f of x squared minus g of x squared times dx. Right, so there's the moment about the x-axis. The moment about the y-axis so m sub y is equal to, so that's going to be, once again, we let n go to infinity. We've got a Riemann sum here, and so it's going to be rho integral from a to b x times f of x minus g of x dx. There's also the mass, so the mass of the lamina is, so that'll be a little m, and it's equal to, so it'll be rho integral from a to b f of x minus g of x dx. So we've got three formulas that we will need in order to compute center of mass. We need the moment about the x-axis, moment about the y-axis, and then the mass. Once you have those three quantities, then we can define the center of mass of the lamina. So, the center of mass is the point x bar comma y bar, where x bar equals m sub y divided by little m, and y bar is equal to m sub x divided by little m. Now, one thing to notice, when you set up these fractions right here, so I'm going to have an m sub y divided by little m. Okay? So imagine when you compute this fraction divided by this fraction, notice what happens. We will have a row in the numerator and a row in the denominator. Those are going to cancel out. Right? And so yeah. So in fact, I want to actually set this up, and I don't want to lose my formulas here yet. Okay, I'm going to put it right here. Let me put it right here. So observe that x bar, so I want to think about what this computation is. Let's see, so x bar is going to have this in the numerator, and then the thing that I just erased in the denominator, sorry I ran out of space there, the rows cancel out. And then if you think about what m is, so let me write m right here, it's rho times integral a to b f of x minus g of x dx. If you take rho out of there, notice you have this integral right there, and what is that? That is exactly the area of the region. So here's a way to think of this. X bar is equal to 1 over the area of the region times integral from a to b x f of x minus g of x dx. Also, y bar, well, let's see, y bar is going to be this, where the row cancels out, divided by the area also, and so it will be, see how they write it in your book? Yeah, a little 1/2. It'll be a 1/2, or let's say 1 over 2a integral from a to b, and then we'll have f of x squared minus g of x squared dx. So there's the formulas that we have. Now, one more piece of terminology. What we have right here, right, we've got this, some region. And when we take this region and imagine it as being some sort of thin plate, right, piece of metal that's been pounded flat or something like that, right, and then if we were to take this object out and find its balancing point, we call that the center of mass, right? It's the spot somewhere in here, x bar, comma y bar, where you'd find balance. Now, so that's called the center of mass. There's also this term that's called centroid. And centroid is essentially the geometric counterpart of the center of mass, right? Think of center of mass as a physical object, a physical quantity, where the centroid is a geometric quantity. It's exactly the same computation in the geometric setting. So when a problem says find the centroid of this region, what it's saying is find the center of mass, but don't think of this as an actual piece of metal. Just find the the centroid. So these two terms can be used interchangeably and are used interchangeably in this book. Okay, so let's try an example now. So let's find the center of mass. Of the lamina occupying the region y equals x and y equals x squared if the density is given by 2. Now notice, I mean, this is kind of weird. The center of mass and the centroid, first of all, are used interchangeably. Think of centroid as a geometric thing, center of mass as a, sorry, I said that, yeah, center of mass is a physical object or physical quantity. But in any case, density doesn't matter. So in your book, when they word the question and say, find the center of mass, they'll give you a density, but notice it just cancels out so it doesn't show up in the formula. And then in other problems, they're just going to say, find the centroid, in which case they don't even mention the word density, right? Because then it's just a geometric quantity rather than a physical quantity. So at any rate, in our computation, we don't even need that fact. I just put it in here because in your book, when they ask you to find the center of mass, they're going to give you a density. Just be aware you could ignore it. Okay, so now what do I need to do? Well, let's just draw the picture real quick. So I've got the line y equals x. I've got the line, or the parabola y equals x squared. And so what we're looking for, right, is the center of mass of that thing right there. Right? So if you can imagine taking that shape and taking it and holding it, what we're trying to find is the balancing point. And so we just need to use these formulas right here. So let's compute each one of them separately. So let's compute m sub x, right? So that's going to be a 1/2 integral from, notice these intersection points are at 0 and 1. So it'll be 1/2 integral from 0 to 1. And then what are we doing? We're doing x bar, so that's going to be a 1/2 top function squared. So that's an x squared minus x to the 4th dx. And so we can just bust this out real quick. 1/2 times x cubed over 3 minus x to the 5th over 5, and we're going from 0 to 1. So that's a 1/2 times 1/3 minus 1/5. Common denominator here is 15. So that's going to be 5 minus 3, which is 2, which cancels, and so we get a 1/15. And then m sub y is going to be integral from 0 to 1 x times, and you know, officially I should be writing in the row here, but it doesn't matter. X times top function minus bottom function, integral 0 to 1 x squared minus x cubed dx, which is x cubed over 3 minus x to the 4th over 4, going from 0 to 1. That's equal to 1/3 minus 1/4, which is 1/12. And then the last thing we need is the mass, or the area. So m is going to be integral from 0 to 1 top function minus bottom function. And that's equal to an x squared over 2 minus x cubed over 3, going from 0 to 1, which is 1/2 minus 1/3, which is 1/6. So now what we have is x bar is going to be 1/12 divided by 1/6, which is 1/2, and y bar, did I miss my 1/2? Oh no, I got it. y bar is equal to m sub x, which is 1/15 divided by 1/6, which is 6/15, which is 2/5, 2/5. So let me just quickly redraw that picture. So let's see if our answer actually makes sense. So we had the line y equals x, and then we had the parabola. And so what did we say? We said x bar is at 1/2, right? So right in the middle. And then y bar is at 2/5, which is a little bit below 1/2, right? So hopefully that makes sense, that the way this thing is shaped, there's a little bit more stuff in the lower portion right here. And so it would make sense then that the y coordinate is a little bit below 1/2. Okay, so let's try one more example. And this one will phrase in terms of centroid. So what I want to do is find the centroid of the region bounded by, so the region enclosed by the graph y equals square root 1 minus x squared and the x-axis. Hopefully you recognize the graph of this as the upper half circle of radius 1. And so our picture looks like that. That should be symmetric. The way I drew this is maybe a little lopsided, but there's the idea. We want to find the centroid. So if you imagine taking a half circle, cutting it out, holding it horizontal, and then finding the balance point, right? That's what we're looking for. Now, a couple of things to notice. First of all, because the density is uniform, using symmetry, we can shortcut the process. We can say, oh, x bar has to be right in the middle. So let's say using symmetry, x bar equals 0. Next, okay, so now we need to compute y bar, and we know that y bar is equal to, well, okay, so it's m sub x over m officially, but we know that that is going to be 1 over 2a times the integral from -1 to 1, top function minus bottom function. So, sorry, top function squared minus bottom function squared. So it'll be a 1 minus x squared minus 0 squared dx. And this A, that's the area of our region. Our region is a half circle. That has area. Well, let's see, what's the area of a half circle? It's pi times the radius squared over 2. So in this case, we just get pi over 2. So this will give us 1 over pi, integral from -1 to 1, 1 minus x squared dx. And so that's going to equal 1 over pi. So now let's compute the antiderivative. We get an x minus x cubed over 3, and we're going from -1 to +1. So that's a 1 over pi times, let's see, when I plug in the upper limit, I get a 1 minus 1/3, so that's 2/3. And then we subtract away the result of plugging in the upper limit, and that's a -1 plus 2/3, so it'll be minus a -2/3. So this is going to give us 4/3 over pi. So 4 over 3 pi. And what is that? Well, it's, 4 divided by 3 pi is somewhere around 4/9. It's a little bit less than 1/2. And so hopefully that makes sense, right? That y bar is somewhere a little bit below, right, the midway point right there. Sorry, I just stepped out of the shot there, but right, so a little bit below. Okay, so that's enough for today. So we've learned this idea of center of mass, which incorporates the ideas of moments and mass. So in the end, at the end of the day, it's just some formulas to remember, right? I want you to understand where they came from. But when it comes to computing center of mass or centroid, it just amounts to computing 3 integrals and setting up the appropriate fractions, right? So in one sense, me asking you a center of mass problem on a quiz or on a test is just a way for me to get you to compute 3 integrals. Also remember, you can make use of symmetry and geometry to simplify some computations. You're absolutely welcome to do so in any problem for which it's appropriate. Okay, see you later.